This is the 3D Pod, your number one source for 3D printing news, analysis, and insight from 3dprint.com. Now, here are your hosts, Joris Peels and Maxwell Bogue.
Hi, everyone. This is the 3D Pod, and my name is Joris Peels. And as always, I'm here with Maxwell Bogue.
Hey, everyone.
And yeah, today we have something really special because we're doing our first collab. Yes, we're hip, just like the children's. So we're hip with a collab with another podcast with another 3D printing consultant. And that's with Mike Vasquez. Mike Vasquez has his own 3Degrees podcast. And he's also a 3D printing consultant. He's got a degree from Loughborough, degrees from MIT, and he's doing a lot of optimization and consulting on 3D printing processes and stuff. So yeah, really looking forward to talking to him today. So welcome to our podcast, Mike.
Thank you very much. I'm excited for the conversation today.
Yeah, and also I guess we're going to be in your podcast as well, so that's going to be quite new for us as well.
For sure, cross contamination.
Yeah, exactly, something like that. I'm just so Mike, tell us a little bit how'd you get involved with 3D printing first off?
Sure. So my kind of career in engineering really started because I like to play baseball. So I played baseball growing up in kind of elementary school, high school, into college. And one of the things that always excited me was that really interested me was that every year it seemed that the baseball bat companies would come out with a new type of baseball bat that was made of a different material. One year it was graphite, one year it was aluminum, one year it was carbon fiber. And I thought to myself, like, wow, like somewhere someone's job is to come up with new materials for baseball bats. And I thought that was awesome. I'm like, I want to do that job. And so in kind of high school and into college, I got really into material science and was still playing baseball and said like, hey, like, can I explore this a little bit more? And ended up when I was at MIT finding this lab called the Sports Innovation Lab that was doing kind of research work for sporting goods companies like Rawlings and bike companies, because we had a wind tunnel access and things like that. And it was really my first experience in terms of hands-on practical engineering applied to materials. And so we designed padding and things like that. And as I got further into that, some of our projects started to involve 3D printing. And one of the things I really learned quickly was that, and this is the kind of early 2000s timeframe. So 3D printing certainly wasn't as mainstream as it is now. And the access to the machines wasn't as widespread. And for the most part at the time, it was really early adopters using it. So aerospace, medical to some extent, and a lot for prototyping. But what I quickly learned was that 3D printing, or one of the other industries that was heavily involved, was the sporting goods industry, because they have a lot of the same requirements that an aerospace company has. They want to make things lighter, faster, stronger, use the same type of materials. But the really good thing is they don't have the regulation. And so they're willing to push the envelope and try these new technologies. And so kind of got involved with some footwear companies like New Balance doing some 3D printing work, and then ended up going across the pond to Loughborough University in the UK, just north of London, to do a PhD focused on materials development. But that was partnered with both EOS and Burton snowboards. So I was doing a lot of work in developing elastomer materials for 3D printing powders and kind of developing that way. And so kind of getting into the industry from a slightly different perspective than many others. So that's kind of how I got my start.
Yeah, and now you're doing like 3Degrees. And what do you guys do at 3Degrees most of the time?
Yeah, so I started 3Degrees in 2012, so almost 8 years ago now. And this was right after I had finished my PhD. I'd done a lot of hands-on work and running machines and a lot of different technologies. And when I came back to the US, realized that, hey, like, this is an interesting technology. It's got a lot of challenges and question marks for companies that see articles about it and see other competitors using it. And there's really, at the time, there were very limited options to kind of getting a third party kind of technology engineering focused approach to evaluating the materials, the processes, how do you scale it, what are the business applications, and so with 3Degrees, kind of the idea was we can serve as a partner for organizations that are going through that process and both understanding kind of production technology and scaling it to large scale systems and facilities. So really what we do is we focus on kind of working with organizations, both materials companies, end users, and OEMs to help them understand the technology and move it into a production mindset. And so we've worked with about 60 companies, a wide range of industries to help them do that, and have had a lot of fun and learned certainly quite a bit in exploring that. So, I mean, I didn't know the first thing about running a business when I first started, and there's probably a lot of mistakes that I made going along the way. So it wasn't all sunshine and rainbows, but it was certainly for me, being an engineer, kind of lifeline engineer, was a steep learning curve to learn to sell to different companies and talk to big companies and trying to navigate who's the right person. So for me, it's been very rewarding and growing in a lot of different ways, both personally and professionally.
Okay, that sounds like a lot of fun. And what's like if you look at of course you'll take on a bunch of different projects, a bunch of different type of things. Like, what's your favorite type of project to do?
I really like the material side of things. And so one of the things that is really exciting from my perspective is being able to kind of match the right material or modify material to the right application. And we've done quite a bit of work in the sporting goods realm, both in footwear as well as some other applications like cycling and things like that. So I really enjoy kind of the hunt, so to speak, of finding the right application that fits the right technology, that fits the right price point. Because, I mean, as you guys know, it's one of those things where it's clearly not a one size fits all technology. There's a lot of hype. There's a lot of BS in the market. And so from my perspective, like, I'm the first one to say, like, 3D printing is not the right application for this. But at the same time, there are useful applications for the technology if people are willing to be a little bit not riskier, but more open-minded on kind of the timelines, some of the costs, and the realities of where the technology is. So
I was just saying, do you have a favorite material though? And that, like, as a material scientist, do you have a preference towards metals or plastics or any of the above, or specific material? I know Joris loves PCL, for example.
I don't. I mean, I've never been asked what's my favorite material. I guess one of the first things I ever did kind of early on, and probably has a literal soft spot in my heart, is I did a lot of work in developing elastomer materials for powder technologies like MJF and SLS. So some of the early TPU materials that we collaborated on, it was like 10 years ago at Burton, are now just getting into the market, which is exciting. But it just opens up some different applications, and they're still growing in that space. I think there's a lot of runway, but it's still pretty early, and there's a lot of differences between that and, say, like a PA12 that is still the dominant player.
I love, like, TPU for sintering. I think it's a really, really exciting material. I think like when we saw that happening, there's a bunch of people working on it, of course, like Lehman and Vos, I think, were the first to come up with it. And then who else? A bunch of people come up with it, but generally, like, no one's really, it's just a nascent material, as in, like, it could be used in production. It could be used in millions of parts. Do you really think it has that kind of potential?
I think I don't know, millions of parts. I think there's certainly good applications for it. What we were looking at was, and I think what's really exciting, is the ability to kind of change the hardness, the durometer within a build. So you have a lot of potential to, depending on how much you sinter it and what the energy parameters are, you have some ability to make some of those almost multi-material or almost gradient type of materials. And so I think the simple applications, people always think of like gaskets or little kind of
living hinges.
I mean, padding for shoes or protective equipment. I think those are quite interesting. They're still pretty heavy, even like with some of the designs. If you've ever seen some of the 3D printed elastomers, I think my main gripe with them is they're still a little bit on the heavy side. But I think with design and with different chemistries and different approaches, you can make it a little bit more efficient. And certainly there's also some, speaking more on the polymer or the powder side, there's some excitement in the fact that you get at least some of the early elastomers and TPUs that we were working on, the ability to not have to recycle as much or kind of blend back into the SLS process or MJF process, which is still one of those things that, I mean, if you're throwing away 30-40% of the material at the end of the day and can't reuse it all, there's some cost to that. So the TPUs don't have some of the condensation chemistry that the nylons do when you hold it at the elevated temperatures and MJF and laser sintering.
I got a suit jacket made out of TPU.
Yeah?
I made a suit jacket out of TPU.
Okay.
Like my wallet and phone case. Yeah.
Okay.
I wore it to a CES one year.
Okay. Well, you need to watch out with the fumes, huh?
Yeah.
Maybe it's too late, but it's not great. It's not great. But okay, I love TPU. I think for one thing you highlighted, I think padding. I love the idea of like customized, like for example, like the headrest of a car or a customized backpack backing, or like for gloves, like kind of customized like kind of inserts for gloves and things. I love it for those kind of things. Do you see like this mass customization being enabled by such a material like TPU, or do you think that's a bit too far off at the moment?
Yeah, I don't see any reason why it can't be. I still think just generally it's not as widespread of a material. It's probably on kind of that second tier of material being used in certainly the plastic space. But I think it's got a lot of potential. I think with the unknown that are still out there, we're actually doing a lot of work with this is kind of what do the long-term properties look like? We know like SLA and some other materials, like if you leave them in the sun too long, even if they're dually cured, like you're going to get degradation. Similarly with this, like some of the long-term fatigue or surface finish, like what are the long-term implications of that? And that goes back to what you need it to be. Is it something that you're going to take out of a box every 3 years and you're going to use, or is it going to be kind of regularly used on a car dashboard for 3, 4, 7, 8, 9 years, and it's going to go through temperature and differences. So I think there are going to be certainly no shortages of applications for it. It's again just coming back for like what's that second layer of material characterization that you have to do to understand it, and that's still something that pretty limited in the industry. I mean, there's a little bit of literature on long-term effects, but even the standard data sheets that you would get from many of the vendors, like they'll give you tensile properties, they'll give you some shore hardness, but that's at one printing parameter in ideal conditions. You don't know what conditions it was tested in necessarily, and does that align to what your end use application is. So I think there's a potential there. It's just a matter of kind of curate a little bit more to say, okay, this is good for these types of environments and temperatures and so forth.
I think it's a good point. I mean, I think it's well known about SLA getting brittle and stuff like that, and UV degradation and stuff like that. But for example, it's less well known. I think is just, for example, standard PA parts, they degrade as well, especially when they're put under repeated stress. And like everybody's always like, you guys mentioned live hinges and things like that. And hinges, I kind of shy away from that kind of use in a long-term scenario because I think that the part will degrade. And that's in the material we understand the best, like PA12. And then I think it's a good point that in like more exotic, or for us more exotic stuff like TPU, it's kind of weird calling TPU exotic, but in that kind of a scenario, you have to really, there's one thing having material on Tuesday, and there's one thing having material like 5 years later. I think that's a really good point.
Right, and it's still kind of a question mark of like what sorts of testing do you need to do with that material? I mean, there's a lot of historical literature on injection molding and things like that, but you're going through different temperature regimes when you put it through SLS or MJF or other printing technologies, and that's going to impact it. How many parts are in the build? What state was the powder in? What was the post processing that you did to the parts? And then where's it going? I think the other thing to remember about kind of TPUs and elastomers in general is that they have a different glass transition than the PA12, which is certainly lower, and so you get closer to that state where it's not quite, I mean, you're getting into some movement of the molecules and some of the stability breaking down at lower temperatures. And so you have to just be careful about that, especially in applications that might experience elevated temperatures. But from our experience, I mean, engineers and the folks in kind of on the end user side, for the most part, it's a kind of double-edged sword. Like they generally know what they want in terms of specification, but there are also a lot of cases where there's a specification written for an existing manufactured part, and if you were to ask the engineer why they needed glass transition temperature or melting temperature above 120 degrees, they probably couldn't tell you if it's an older part or if it's a more legacy part. And so I think there are some ways that people could be more open to materials if the database and if the testing is more expanded on the long-term properties.
The tooled parts have the same kind of limitations in some way, like they're just a different number, but a living hinge on a injection molded part is still spec'd for something, 10,000, 100,000 moves before it breaks. So it's
absolutely
same thing, different material. So yeah, you get different properties.
Right. And I think people are trying to become more comfortable with, I mean, all materials will fail after a given point in time or after certain stresses or temperatures or chemicals that are kind of leached into them. It's more kind of understanding what is the failure going to be and how long. And so I think it's okay to have a material fail. It's just, okay, was it an expected failure, or is it something that we can mitigate or engineer around, or have an appreciation that, like, hey, if you're a shoe and it's going to degrade over a year, okay, like most people replace their shoes in about a year. So I mean, it's not the end of the world, right? There's some level of either consumer or industrial expectation that there's a replacement cost to these. So it's just more understanding what that might look like.
But I think we do have a problem in our market that, well, for example, like the Young's modules degrading on sintered parts or stuff like that, is unexpected, right? It doesn't really belong it isn't calculated in the same way, or the behavior is not the same as a molded part. So they wouldn't be expected. It isn't like a linear thing that'll last completely 10,000 times before breaking, because that's what they're used to doing, right? So the test has to be different, right? And that, I think, is going to be a really big problem if you come to people and say, hey, we have new exotic testing, right? And then they're like, well, wait a minute, you have new standards, new everything, you're making this up as you go along, and we kind of are, So I think, I do think it's an important point. And I think there's also a problem, or it has been a problem since the beginning of our industry, where people seem to think that because we can make a shape, it's automatically functional. And a ton of the shapes we showcased to the public and to the media, and also just on trade shows and things, are not functional parts. And people have this idea that they're functional. And there's a huge gulf between being able to make something and being able to make that a functioning shape.
Right. Yeah. I mean, it's a ton of work to go through the entire end-to-end kind of production readiness process of getting a part ready for actual use. I mean, you've got, design as a whole can of worms that you have to think about, putting it in, selecting the right materials, doing all the material testing before, during, and after, and post-processing inspection. And I think that's, it's one of those things that it's underestimated how difficult that can be. And it changes depending on the application. If it's a consumer product, maybe there's a little bit less where you're focusing more on the appearance, right? Versus in some more industrial settings where mechanical strength is required or long-term stability, that changes the focus of all the testing that you're doing. So I think you're exactly right, is that the the functional form or just the shape of the part is really what 10% of the story. Probably it's like the iceberg. Like you only see 10%, but all the stuff that's behind it is really what kind of pushes it into a position to make it an effective manufacturing part. And all that, I mean, at the end of the day, like that costs money. It costs engineering time. It costs testing time. It costs development time and machines and materials and all that. So sometimes I would say that like some of the cost models that you see, like, okay, we can get, like in an ideal world, we can cut 30% weight off and it saves us this amount of fuel. There's a high cost up front for the development of that, getting it to either a manufacturing ready part or something that could go into production.
Just generally, I think that's interesting. Are you also, one material I'm also like super excited about is polypropylene. Like for FDM, I loved it. I think it's Clariant that came up with it first, if I'm not mistaken. Maybe somebody else had it, I'm not sure. But Clariant for FDM had it, Clariant, which is now DSM, which is now Covestro. They had it, and then now also I think MGF or HP has it as well. And I'm really excited about that because I know there's so much polypropylene, and also I love the functionality of it, the softness of it. I love it for like sports equipment again. Are you as excited, or you don't as excited about polypropylene?
I think I'm excited from a different perspective. Well, I think the potential for using, I would say, more conventional plastics is exciting. Certainly MJF and SLS and FDM to an extent have process limitations that there's a reason PA12 is so widespread. It's because it works well in the process. But if like PA12 is a specialty material, I know Evonik makes tons of it, and Arkema and things make probably tens of tons or hundreds of tons at this point of material every year. But in the broad scheme of things, like you ask a general plastic supplier, do they have a lot of customers using PA12 or do they make a lot of it? And they're like, no, like it may go into dishwashers. I think is the main use of PA12, but it's very special.
Makeup additive. It's like the stuff that makes your makeup kind of creamy.
Yeah.
Lipstick. Yeah. There's a lot of it in lipstick.
And
powder coating.
Right. But at the end of the day, it's not a huge.
Compared to polypropylene or HDPE or whatever. Right.
And so I think like more broadly, I mean, yes, I think there'll be nice applications like on the end use side, but I think what I'm interested to see how it plays out is, okay, can you get more, I'd say, kind of generic polymers into these systems and start messing with some of the costing models of what exists in the market today, right? I think what we're seeing is the material cost for certainly the powders really hasn't changed in 10 years. I mean, if you buy at volume and things like that, it changes a little bit, but you're still getting these markups where you look at an injection molding grade of really any material. It's going to be most likely it's going to be under $3. I think nylon 12 is like $8, like as a pellet, somewhere around that range. But once you start getting into how much does it cost to powder, like put it into a powder form or kind of get it ready for SLS, like the markups that these manufacturers are getting on that is still pretty significant. And yes, I'm not saying like they shouldn't make a profit and like that is know-how in the process of kind of producing a polymer.
Just to give you an idea, like, the pricing is like, it's about $30 per kilo for volume if you're doing it directly yourself. If you're doing it from like directly or indirectly at semi-volume, like your service bureau guy, you're going to be paying anywhere from $65 to $95 a kilo.
For sure.
For the stuff that's around 10, 12.
Yeah.
And then effectively you're going to pay about anywhere from 30 to 50% more because you're going to toss that away. So yeah, you're looking at like $120, $150 a kilo per powder.
What is kind of developing with these new materials is, yes, I think some of the functionality is exciting that you can kind of open up some of these different ranges, but like and this is my opinion, but like the reason you see more materials is because the conventional polymer injection molding companies of the world see what the companies like Evonik and others have gotten in terms of margins for these types of materials. So, I mean, that's a pretty good margin for, right? And so so I think my sense is that
DuPont and these guys are like, I want to get in on this.
Right. But the challenge is they want to do it for these conventional materials, right? Like maybe like a polypropylene or TPUs and things like that, where it's so cheap to get that conventionally that like that's also one of the reasons, not just functionality, that they're used. It's like because they're cheap, right? And if the assumption is for these big materials players to get into the market is that they're building their business models off of getting these huge margins, I don't know how long that's going to last or kind of expand into kind of new applications if like the cost modeling just gets harder with a really expensive generic material like a polypropylene or others. I'm using polypropylene as an example, but there are other kind of materials that probably fit into this category. Like it's harder to make an apples to apples justification for switching over from a 3D printed component from injection molded. Whereas it's a little bit easier with PA12 because you get like it's already expensive from a pellet form. So the injection molding cost is a little bit like the gap isn't as big, even though there's a big margin gap. But I think if you get into some of these other materials that conventionally are very cheap and now they're like at the same markup range, I think you're going to have some issues.
I don't know about that though, because like I think I understand the point, but I think ultimately it depends on the functionality that you can achieve, right? So the ultimate business case of an ULTEM or a peak part for a satellite or like a RF transmitter on an airplane or something, that business case is going to be much better. You know what I mean?
Sure.
And then we're talking about expensive that, I don't care what they make it out of. They don't care. It's not like these guys, like Raytheon is not like, hey, you're only paying $6 a kilo for this stuff. They don't care.
Oh yeah,
they want to have like the best antenna for an aircraft,
Sure. So I agree with you on that point. Like Peak and Ultem, I mean, I would put those in slightly different categories, right? Like those are the highest performing material, like thermoplastics that you have, and so they're expensive, whatever route you go. I think more what I'm thinking is kind of the lower end materials that are the PPs and maybe PET and things like that are fairly kind of generic at this point.
But I'm saying that there is never a business case for a one-on-one replacement of 3D printed parts. Sure. There's never. So the only reason it's going to work is if we make like a TPU backing for a backpack that's individualized for your kid, right? Just exactly the size of his back, and he's more comfortable and has less back problem. That's the only way that we can make this happen. It's not like they're going to say like, now with 3D printed backs, we're going to pay 20 times as much. I don't know. I've had so much of these struggles with these base economics of the thing. But I'm like, let's look at the user value of the ultimate customer. How do we help you sell more? How do we help you? So that's what I meant. Like not only with these like high-end engineering materials like Peak and stuff, but also just like, what does the customer want? And let's make that customer happy. And then everything else will fall into place. You remember the pump things we had on shoes? Oh God, this is like going to age everyone.
Yeah.
I think it was the 90s, right? Or the late 80s, early 90s.
A bunch of kids are going to have to Google that. Like, what? Pump on a shoe? I mean, that was like, it was nonsensical. It didn't make sense. It was much more expensive for them to do. It added many more parts and a lot of complexity.
Pure marketing.
Yeah, but it did really well. I mean, I'm saying, and that's the kind of stuff we should be selling to people, not like it's 3D printed, so it's awesome.
Right.
Right.
Yeah.
I think there's a lot of value.
Yes. And ultimately the customer probably doesn't care how it's manufactured, right? Like, do you really care like what soldering technology was used on your phone, right? Nobody cares, right? Like it's the value.
Only the engineers, only us engineers care about what soldering technology.
Hand-laid Ultem sheets or hand-laid Kapton.
Exactly. So I think it's a little bit overhyped in that sense of like, does it need to be 3D printed and ultimately who cares, right? Like, what value does it give me as the customer?
Yeah, but that to me is like the economic thing. And so I'm not like, the conversion pricing of that kind of thing is maybe, can we help them sell more backpacks? And I think we've never, as an industry, we've always kind of let the customer lead us. And I think that's led to some brilliant things. I mean, we wouldn't be doing turbines for tanks. And we wouldn't be doing turbines for jet engines and propeller engines if it weren't for some crazy customers, and definitely the hearing aid thing, and also the Italian guys, all the Italian guys that made the the hip implant thing possible. That was just insane from their point of view, how long it took for them to make this happen. So we have been led by customers to success, but a lot of things I see customers kind of leading us into nowheresville, you know?
Sure. Yeah, that's fair. I think there's a lot of exploration of the technology and innovation for the sake of like our competitors doing it, or we see that this VP wants to invest in 3D printing, and so people go and buy a machine. And so there's still a lot of that.
Corner.
Yep.
Yeah, there's this campus kind of set up, and a colleague of mine went there, and he said they're making door stops. So they had like SLM machines, like our pattern bed fusion machines. And they were literally making door stops and gadgets and desk gadgets, and that's mainly what they were doing. There was like one build, like a 290 or something.
That sounds like the perfect application for a 12 laser system, right?
Yeah. It was like he just came back like shell shocked. He's like, what? Yeah. And also, you said earlier about this requirements thing. I've had things where I'm like, and about quizzing the customer on the requirements. I think that was a really good point as well, because I've had things where I'm like, the only thing I know from your requirements is you don't know what you're talking about.
Right.
It was like, or they're just like, we had, how do I anonymize this a little bit? We're looking at these customers' requirements, and they were so ambitious that first we were like, oh my God, this is like the visionary stuff we need, big company, big money, big vision, And then we started looking at like, kind of like just some of the underlying things, and it was like, but that won't work. As in it didn't internally make sense, and then the thing just didn't it didn't match up. The volume they wanted, the throughput they wanted was so high that then the material reservoir they had was not commensurate with that. So they didn't even think it through. So I'm thinking a lot of people are just, we need to admit to each other that we're just making this up as we go along,
The flip side of that is I've seen been in some of those similar conversations about the spec. And even if you can convince the engineer or team that you're working on that the spec could be changed or updated or modified, the amount of inertia that it takes to do something like that is probably enough to cancel or severely delay a 3D printed project in many cases from our experience. We don't have an issue with that, but you'd rather find out about that earlier than later. But to kind of re-characterize materials or even specify new printing technology, it's a long effort, certainly depending on the industry.
Just generally, I think we're kind of also coming into a moment in the industry where it's like conventional that, okay, prices are going to come down for everything. We're going to have more competition, and we're going to move to industrialization, right? And we're going to do some mass customization stuff for some industries or something like that. Generally, that's kind of like the feeling that people have. And, desktop printers, I think most people think that at the moment it's not going to happen, although I'm more optimistic about this than I have been in years. But what are your, apart from that, otherwise you're going to repeat the same story that everyone else says, but just generally, what are your feelings about just like how this industry is going to develop in the near term?
Yeah, and I think there's certainly going to be opportunities. A couple things that I've noticed over the last 2-3 years is you've got certainly a push towards industrialization, and that's a number of companies have invested tens of millions, 20 millions of dollars into kind of having these R&D future-looking teams identify applications for 3D printing, and they've come up with a lot of interesting, or handful of interesting applications. I think what I'm curious to see is how the supply chain around scaling production expands. And so what I mean by that is, even if you take kind of conventional manufacturing right now, right? Some of the big automotive, aerospace companies, the brand names, they're really more assemblers than manufacturers, right? They probably make 20% of the parts that they assemble together and put on planes or cars or whatever. The 80% or so other parts, like they're getting in from their supply chain. And I think there's this challenge right now. If I'm a existing supply chain member of some of these big companies that you've seen invest in 3D printing, and they're starting to come out with parts, like what place do they have in the market? Do they need to transfer over from some of their conventional manufacturing, get in additive production capability, what do they invest in? I mean, it's a big investment usually for these small, medium-sized manufacturers. Is that where kind of is the production flow going to go towards them, and what does that evolve as? That's where we've had a lot of conversations on our podcast, and a lot of the work that we're doing now is like, what does that landscape look like for the small and medium-sized manufacturer when it comes to 3D printing? Because you hear the sexy press releases are from the brand names, right? Like in the industry, the people that everyone knows who Ford is, or Boeing, or whoever it may be. But a lot of the kind of work comes, at least in the US, comes from these small, medium-sized manufacturers. And I still think there's a pretty big gap of understanding and potential of where do they fit in, and does it go to service bureaus that have had some existing, they're not really set up for production in many cases. Like that dynamic, I think is what I'm really interested in, and we've been doing some work on the software side to help kind of get some of these small, medium-sized companies ready for that piece as it spills over, if we buy this hypothesis that it's going to expand, which I think in general is going to, but I think it's there's certainly challenges along that way.
I think that's a great market to focus on, just because there's so many of these businesses. And yeah, if we look at a company like Stryker or the GEs and the Honeywells and the Raytheons of this world, they have the heft to do this, right? They can throw 200 engineers at it, or 200, 400 million at it, and they can take the time as well, because it'll give them lasting benefit. But yeah, one of these small to medium businesses, or at least in an American context, small to medium businesses, which are much larger than other people's small to medium businesses. But these guys, do they have the heft to do this? They're going to want to have tools and training, and how are they going to get the people and that kind of thing. So I think that's a really exciting market for you to focus on.
Yeah, and I think it's there's already a lot of kind of interesting stories there, and for the most part, I mean, these are small, medium-sized companies, mom and pop store, like places that probably have less than 50. In most cases, they have less than even 20 or 30 people, but they're making a lot of good parts, and they've done things a certain way. It's been successful. Probably not as digital as like the people like you think like everything's digital thread and manufacturing yet, but they still get it done. And so there's that other dynamic of there's the investment in the machines, materials, know-how, understanding all that ramp up costs, and then kind of what is the expectation as well on the digital side to kind of have part traceability and tracking of those components and managing files. So I think to call it like the plumbing of additive manufacturing still is a lot of stuff to work on.
And definitely, dude, you definitely got a lot of stuff to do there. And what's your personal hope for 3Degrees? Where do you hope to be in a couple of years? Would you want to be a really huge company, or just a really fun one, or really admired, or what's the goal for the business?
Sure. I think it kind of focuses on two things now. One is we've just developed a software tool called Trace, which is with the focus of small, medium-sized companies to help them digitize a lot of their 3D printing workflow, so that you have a kind of a souped up database that allows you to input those key parameters at each step of the process. So we're excited about building that out. We're working with kind of an small aerospace supplier right now, and Renishaw as well, to integrate some of that technology going forward. So that's exciting to build out and to take the business to kind of a different level with some of the software tools. And the other piece is we're hoping to do a lot of work to kind of share some of the different career paths that exist in this space. I mean, like yourselves, we think the industry, while it has its ups and downs and hype, I think at the end of the day, I think there's a lot of exciting stuff and well-meaning people doing work to propel manufacturing forward in the US and globally. And I'd like to help kind of push some of the next generation of people who may not know what's going on in that kind of white, nondescript, windowless building on the side of the highway, and show them that, like, hey, like there's some pretty cool machines that go on inside there. And so that was one of the reasons I started the podcast, I've been fortunate to see a lot of this manufacturing across the country and kind of be hands-on with it, and kind of give people a platform to share what stories, how they got into the career, like what are sorts of technology they're doing, like what advice do they give. So kind of building that out. And then this summer in Chicago, we're helping with some local community organizations targeting kind of 18 to 24-year-olds on the west side and south sides of Chicago, who to kind of get them educated into what does a career in 3D printing look like? And so matching them up with some mentors and some hands-on kind of experience with some production machines, some tours of major manufacturers that are using the technology in the area, to kind of show like what the potential is. Because I think still, if we live and breathe this industry every day, and so we know kind of what the nitpicky challenges are, but from someone from the outside who still may think that manufacturing's a dirty job, or kind of you envision what it looks like. And if you watch some of the older movies from the 60s, 70s, and 80s, kind of what manufacturing is portrayed in, I think that really hasn't changed. And so showing people what the potential is and what kind of a career could look like is really exciting for myself and as well as the team members on our organization.
Awesome, man. Mike, it seems like a really worthwhile pursuit. So yeah, that was a wonderful episode again of the 3D Pod and also of 3 Degrees. So if you're a 3D Pod listener, go check out 3 Degrees and vice versa. And we'd love to hear some feedback and some stuff. So thank you very much for being here today, Mike.
Thank you all.
Yeah. Thanks.
And Max, thanks for being here as well.
Always.
And this is my name is Joris Peels, and I was here today with Maxwell Bogue and Mike Vasquez on a combined episode of the 3D Pod and 3 Degrees. So I hope you really enjoyed it, and thank you so much for listening. Bye-bye.
You've been listening to the 3D Pod. For more information on what you just heard or to subscribe, visit www.3dprint.com or follow us at 3dprint_com.